In previous class, we were discussing about the circle diagram. We got to know how to draw the circle diagram using no-load test results and block rotor test results. We also got to know how to calculate different parameters of the induction motor. Now today we'll see how to calculate the maximum quantities. How to calculate maximum quantities. Okay, for this I need to have the circle diagram. This is voltage axis, this is current axis. Now this is point O, this is O dash. Now from here we'll be drawing a horizontal axis. Now here from this point we'll be drawing the ISN, and I'll be naming this point as point A. Point A. Now join O dash A. Now this line is output line. To this O dash A output line, draw a bisector, bisect this output line perpendicularly. Now join, extend the line till it reaches the horizontal line. Now name this as point C, and keeping C as the center and O dash C as the radius, draw a circle, draw a semicircle till it meets the horizontal line at point B. Now to calculate few maximum quantities, like this is about the circle diagram. Now to calculate the maximum quantities, the first point I am considering here as maximum output. Now maximum output, since this is the output line, okay. Now maximum output can be drawn like by drawing a line parallel to this O dash A. To this O dash A, draw a parallel line which should also be a tangent to the circle. That means obviously this point here, okay, and name this point as M. Now draw a perpendicular line, a vertical line till it reaches the horizontal axis, and name this as and name this particular point on the output line, the intersection of this vertical line with the output line is named as point N. Okay. Now we know that the above this point is nothing but the output. Okay, because here we knew that this vertical line, this entire length is giving us the losses. So above this is entire output. So here this is the line extended from the point A. So above this line is entire thing is output. So the length mn, the length mn is giving us the output. Length mn is giving us the output. Multiply this with the power scale. We'll be having the maximum output in terms of watts. Now the second point to be calculated is maximum input. Maximum input is nothing but the point which is the maximum point of the circle. Now suppose if I draw a horizontal tangent to the circle, here it will be that point. Okay. Now from this point, draw a vertical line till it reaches the horizontal axis. Now this particular line, and I am naming this point as point L and L dash. The length LL dash, this particular line, this LL dash is giving us the maximum input. Length LL dash into power scale will get us the total maximum input power in terms of watts. Now the third point is maximum torque. Now here we know that after calculating the point E or the ratio AE by EF, we can mark the point E here on this line, and we will be joining the points O dash and E, and this is nothing but our torque line on the circle diagram. This is torque line. Now to calculate the maximum torque, draw a parallel line to this torque line, which should also be the tangent to the circle. Now if I draw the parallel line to this torque line, which will be coming somewhere here, this is the parallel line which is also a tangent to this torque line. Now the point here, the tangent point here on the semicircle is nothing but the maximum torque point, and I am going to name that as point J. Point J is nothing but our maximum torque line, maximum torque point. Draw a line vertically down till it reaches the torque line and name this point as K. Now anything above this is nothing but the output of the machine, okay, output of the shaft. So this is the torque given by the motor. So this is the maximum torque, this is the maximum torque of the machine. So now the length JK is giving us the maximum torque. So length JK into power scale will give us the maximum torque in Newton meter. Next, the fourth point, the fourth maximum quantity is nothing but the power factor. Now, to calculate the maximum power factor, we need to just draw a line tangent to the semicircle starting from point O. Okay, so to this, if I draw a tangent, it would go like this. Now this point is the point to get the maximum power factor. Now from here, draw a line vertically down till it reaches the horizontal axis, and I'm going to name it as point P. Sorry, I'm going to name it as point H and this as point I. Now actually we need this angle. This is the angle to have the maximum power factor. Either we can directly note it down using a protractor, or else you just measure the length of HI and OI, so that considering this as a right angle triangle, the cos phi, the power factor, can be calculated directly by doing HI by OI. Sorry, that is, this is the right angle triangle, this is OHI is the right angle triangle, and the cos phi, this angle and this angle will be same, so the cos phi is base divided by hypotenuse. So it is cos phi is equal to base, that is HI, divided by hypotenuse is OH. Like this, we can calculate these maximum quantities of the induction motor. Now after this, we are going to check the full load condition parameters. Now, if the machine is run under full load condition, now this is the line, the point A is for full load condition, okay? But here we already know that this AE is giving us the rotor copper loss, and this EF is giving us the stator copper loss, and this FD is giving us the constant loss. So where is the output here? Nowhere, okay? Anything over this, above this output line is the output. So only I said this Mn is giving us the output for the maximum quantity. But for the full load condition, this is the operating point. So now to get this full load condition on the circle and to determine the full load condition parameters, we should be first checking the rating of the machine. Suppose, I'll give you an example. Suppose it's a 5 HP machine. 5 HP is nothing but 3.75 kilowatts. Now this 3.75 kilowatts, okay, the output of the machine is 3.75 kilowatt. That means after subtracting all the losses, the actual output, the machine is giving us 3.75 kilowatts output. But here from the point A, below all these parameters are losses. So adding that 3.75 kilowatts from the point A will get the actual output. But for that we have to extend the line from point A over its head. Okay, now I'll show you how to do that. Now we already know that this length AD is nothing but WSN. WSN is nothing but length of AD, and by knowing we had already calculated WSN, and we also can check down what is the length of the AD, so only we have calculated so-called power scale. Okay, now we know the power scale, we know the actual output of the machine, so we can convert this output into centimeters in the graph sheet, like length of a dash, the one which we are going to extend over its head. Okay, the length of the line which we are going to extend from point A, let me call this as a dash. It can be calculated by doing 3.75 kilowatts divided by power scale. By doing this, we'll get something in centimeters, because this power scale is in watts per centimeter, so watts will get cancelled. So here we'll get this answer in terms of centimeters. So length of a dash can be calculated like this. So for the same length, we are going to extend the line, this vertical line, from the point A. Now suppose that is around 2 or 3 centimeters. For those many centimeters, we are going to extend the line. Okay. Now let me name this point as A dash. Now what to do here is, from the point A dash, draw a parallel line to the output line towards the y-axis. Okay, so draw a line parallel to this output line towards the y-axis. So this is the length. Here I am going to draw a line parallel to this output line, and here it is meeting. Okay, and the meeting point, I am naming it as point P dash. Here I'll mark this. This P dash, the point P dash, is the full load condition point. Okay, under full load condition, this is the operating point of the induction motor. Now from here we'll get this as the output. This is stator copper loss, this is rotor copper loss, because these two are the ratios. This is rotor copper loss, this is stator copper loss. In the same ratio on this semicircle, on any point, this will be the ratio. Okay, this is rotor copper loss, this is stator copper loss. You bring the point anywhere on the semicircle and the ratio remains same. Now here this is the operating point. Over this output line, anything is the output, and this is giving us the rotor copper loss, this is giving us the stator copper loss, and this length is always constant line, always constant losses. Okay, this is about the full load condition. Now let us solve few numericals on this. Now I will read out the numerical statement. Better you people note it down so that you people can solve it along with me. Okay. The numerical statement is, draw the circle diagram for a 20 HP 50 Hertz 3-phase star connected induction motor with the following data. Okay, they have given no load test results and blocked rotor test results. I'll write them down here. No load test results and blocked rotor test results. For this, it is 400 volts, 9 ampere, 0.2 power factor lagging. And for block rotor test, it is 200 volts, 50 amperes, 0.4 power factor lagging. Okay, these are the no load test and block rotor test results. Continue with the question. Determine the line current and efficiency for full load condition using the circle diagram. Okay, now I'll write down the given data completely. They have given the no load test results, that is 400 volt, 9 ampere, 0.2 power factor lag, and block rotor test results as 200 volts, 50 ampere, 0.4 power factor lag. Now they have also given that it's a 20 HP machine, 20 HP machine with 50 Hertz. Okay, and they have asked us to calculate the line current and efficiency under full load condition. Under full load condition. Okay. Now we have all the data here, but here under no load test and block rotor test, they have not given us the power. Okay, they have not given us the wattage consumed. Okay, so now using only this no load test result and block rotor test, we are going to draw the circle diagram. Okay, here from no load test, they have given from no load test, they have given that cos phi is 0.2, cos phi naught is 0.2, so phi naught is cos inverse of 0.2, so phi naught will be 78.46 degrees. 78.46 degrees. Similarly, from blocked rotor test, cos phi SC is given that it is 0.4 lagging. So phi SC is cos inverse of 0.4. It results as 66.42 degrees. So once we know this phi naught and phi SC, we can calculate further parameters. Like now we know this I naught and ISC, and also V naught and VSC. So here we can start with the ISN. ISN equation is VL by VSC. Equation for ISN is ISC into VL by VSC. Now ISC is given that it is 50 amperes. Now VL by VSC is 400, VL is 400, VSC is 200. So this results in 100 amperes. Okay, ISN, that is short circuit current under normal voltage. ISN is short circuit current under normal voltage, which is 100 ampere. Here we cannot conduct the experiment to get to know what will be the short circuit current under normal voltage, because under blocked rotor test the rotor is blocked, it is as good as a short circuit. Okay, under short circuit condition we cannot apply the rated voltage to the machine. Okay, so only we had the short circuit current under reduced voltage. This is not the full voltage of the machine, so this is the short circuit current under under reduced voltage. So only we are guessing, it's a guesswork. Okay, under short circuit current, what will be the short circuit current under normal voltage, what will be the short circuit current. So this is how we are guessing this. Okay, for VSC voltage, ISC will be the current. So what will be the current for regular normal voltage? So for 200 volts it is 50 ampere, and what will be it for 400 volts? It is 100 amperes. Now we have calculated ISN. Similarly, we got to calculate WSN. Yesterday I had given you the equation. The equation for WSN is ISN by ISC whole square into WSC. Okay, so by doing this we'll get it as 27,712.81 watts. Okay, this is WSN. For WSN we can use one more equation. Okay, this is optional, or we can use root 3 VL ISN, because this is WSN, VL ISN cos phi SC. Even if you use this equation, we'll get the same answer, 27,712.81 watts. Okay, now after calculating all these parameters like ISN and WSN, we can start plotting the circle diagram. Just remember the procedure to draw the circle diagram. Take a graph sheet, and better to keep it horizontal or in landscape mode, and draw the axis, y-axis and x-axis. Name this y-axis as voltage axis, and this horizontal axis as current axis. Okay, now we know the I0, we know the ISC, we also know this ISN. So the first point here to draw on the graph page is to draw the I0, from the point O. Okay, from the point O at an angle of phi naught from the voltage axis. Now phi naught is known that it is 78.46 degrees. Now, but before that, for how much length we have to draw, we have to calculate that. So to do that, we should be setting up the scale, the current scale. Okay, current scale. Now let me explain you how to set the scale. Now the ISN is 100 amperes. ISN is 100 amperes. Even this ISN we are going to draw on the graph page, okay? And we know that our graph page is hardly of 20 to 30 centimeter. So the entire diameter should not be more than this 20 centimeter, okay? So only to reduce this 100 amperes into 20 centimeters, I'm going to set the current scale as 1 centimeter is equal to 5 amperes. If I make 1 centimeter is equal to 5 amperes, then this ISN will be converted into only a 20 centimeter line, okay? So with that scale, if I start drawing this I notch, this is I notch, okay? If I start drawing this I notch, this 9 amperes will get converted into 9 divided by 5, that is 1.8 centimeters, okay? This I notch will be hardly 1.8 centimeters, okay? 1.8 centimeters, making an angle of 78.46 degrees with the vertical axis. So keeping the protractor here like this, measuring 78.46 degrees, I'm going to draw, suppose this 78.46 is here, I'm going to draw that I naught from the point O for the length of 1.8 centimeter. So this is O dash, okay, and this angle is 78.46, okay, this length is 78.46 degrees, okay. Now from the point O dash, draw a horizontal line, okay. Now this is about drawing only the I notch. Now draw ISN. By making an angle of phi SE with the V. Now ISN is 100 amperes. Again, using the current scale, it gets converted into only 20 centimeters. Okay, ISN 100 amperes, and if I use the current scale, here it will become 20 centimeter, and with the I have to draw that by making an angle of 66.42 with the V. So again, keeping the protractor here, for the angle 66.42, draw the line ISN. Okay, so 66.42 will be somewhere here, and draw it for the length 20 centimeters. So name this point as point A. Now we should be joining O dash and A. Okay, now this is the output line. This is output line. To this output line, we are going to draw a bisector. So this is the bisector line, okay, and this is point C. This is point C, okay. Now keeping C as the center and O dash C as the radius, draw a semicircle starting from O dash till it reaches point B on axis. Here I'll name this point as point B. Okay, I repeat here. First, we should be drawing this O dash at an angle of 78.46, 78.46. Then from O dash, draw a horizontal line to this horizontal axis. Then for the length ISN, that is 100 amperes, because our scale is 1 centimeter is equal to 5 amperes, convert this ISN into centimeters, that is 20 centimeters. Draw this ISN again from the point O, at an angle of 66.42. This angle is 66.42 degrees. 66.42 degrees. Now join this O dash A. From the point of O dash, join it till reaches A. Now draw a bisector to this output line. This is a bisecting line. This is a bisecting line. Okay? Okay? And extend the line till it reaches the line O dash B. Now this point will be the center of the circle and name it as point C. And keeping this as the center and taking O dash C as the radius, draw a semicircle till it reaches the point B, on the horizontal line. Okay? Now draw a vertical line from the point A till it reaches the horizontal axis at point D, and this is point F. Okay, I have not yet marked the point E because it should be calculated, but since they have not asked us to calculate the rotor copper loss and stator copper loss, no need to calculate this. Okay, we can leave it as it is because they have not asked. Now they have asked us to calculate the line current and efficiency under full load condition. Okay, now the full load condition, just now I had explained you, this is the full load condition, but all this entire length is nothing but the loss of the machine, because this belongs to rotor copper loss, then stator copper loss, and then the constant loss. Now the output of the machine has to be extended over the point A. Now we know that the output of the machine is 20 HP. Output of the machine is 20 HP. 20 HP is the output available on the shaft of the machine. So 20 HP is available, and before that all the losses have been calculated. I mean, all the losses have occurred. After that it is giving us 20 HP. So now 20 HP means 1 HP is equal to 735.5 watts. Now 20 HP is equal to 20 into 735.5 watts. Excuse me. It results as 14,710 watts. Now the output of the machine is 14,710 watts. This is the output of the machine. Okay, only the output of the machine, not any losses. So I should be extending the line from point A above for 14,710 watts, but this graph is in terms of centimeters. So convert this 14,710 watts into centimeters. But this is not the current, okay, this is power. So you should be converting this into centimeters using the power scale. So first should be calculating the power scale. Okay, now to calculate this power scale, we know that this is the total power. Okay, this is the total power, and we also know the WSN. Okay, we also know the WSN. We have calculated that it is 27,712.81 watts, and using a scale, using the scale, just check down what is the length of the AD. Now power scale is nothing but WSN divided by length of AD. Now WSN is 27,712.81 divided by length of AD. That AD is approximately 8.2 centimeters. If I do that, I'll be getting it as this results as 4. 3,379.6 watts per centimeter. This is the power scale, 3,379.6 watts per centimeter. Now this is power scale. We know that the output is 14,710 watts. Now I have to convert this into centimeters. So divide this by the power scale. If I divide that output by the power scale, I'll be getting the length of AA dash. Length of AA dash can be given by 14,710 watts divided by 3,379.6 watts per centimeter. Then this is equal to 4.35 centimeters. Okay, dividing the actual output of the machine, which is in watts, divided by the power scale, 3,379.6 watts per centimeter. I'll be getting this in terms of centimeters, 4.35 centimeters. Now I have to extend this line vertically upwards for the length 4.35 centimeters. Now extend the line for the length 4.35 centimeters, and this point you name it as point A dash. Now this is the output of the machine under full load condition, and these are all the losses of the machine. Okay, now to calculate all those remaining parameters, but this is in the ratio. Okay, this is not the actual point. Actual operating point will always lie on the semicircle. Okay, so only draw a horizontal line from the point A dash to the output line. Draw a parallel line to the output line from the point A dash. So here to this line, draw a horizontal line. So here I have the horizontal line till it reaches the point P. Okay, now bring this down, draw a vertically downwards line and mark this point as Q, this point as R, this point as point S. Anything above this line is output, and this is total copper loss, and this is total constant loss. Okay, now they have asked us to calculate the line current, the efficiency and the efficiency under full load condition. The line current can be easily calculated just by drawing a line from point O to P. Okay, draw a line from the point O to point P and measure the length of the OP. Now the first point to be calculated, that is line current, which is equal to length of OP into current scale. I'll write it completely, current scale. Okay, now the length of the OP is 6 centimeters. Now the current scale, we have taken it as 1 centimeter is equal to 5 amperes. Okay, 5 amperes per centimeter. So centimeter you cancel, it is 30 amperes. That means under full load condition, the machine will be drawing 30 amperes. 30 amperes. Now the second point they had asked us to calculate was the efficiency. The efficiency is nothing but the output of the machine divided by the total input of the machine. Output of the machine is anything above this output line is output of the machine. So it is efficiency is equal to PQ. We'll directly calculate the percentage efficiency. Now the output is PQ and the input is the total thing, output plus all these losses. So this is output, this is total copper loss, this is constant loss. So divided by PS into 100. So the length of PQ by PS is, the length of PQ is 4.2 centimeters and the length of PS is 5.2 into 100 will get us 80.75%. This is percentage efficiency of the motor under full load condition. Okay, hope you people understood the numerical. Okay, I will repeat this. I'll repeat with the calculation of power scale. Okay, here after drawing the circle diagram, we can easily check down the length of the AD. The length of the AD is equal to WSN. Okay, and we have already calculated WSN. Okay, which is equal to 27,712.81, and that 27,712 is here. Okay, the length of AD. So only we can easily calculate the power scale. Power scale, scale of the power is WSN divided by length of AD. If I do that, I'll be getting the power scale as 3,379.6 watts per centimeter. Now after that, they have asked us to calculate the few parameters based on the full load condition. So here this is WSN. Okay, WSN. This belongs to all the losses. Okay, so to show the output, I should be extending this line over its head. Okay, so from the point A, I should be extending the line vertically upwards for the output. Now we know that the output is 20 HP. 20 HP is the actual output available on the shaft of the machine. So 20 HP is nothing but 14,710 watts. But now I cannot show this 14,710 watts into the graph page, because graph page is in terms of centimeters, in terms of length. So convert this 14,710 into the length, okay, in terms of centimeters by using the power scale. We know that power scale is 3,379.6 watts per centimeter. That means for 1 centimeter it is equal to 3379.6 watts. So for this length, check out what is the centimeter. So 14,710 divided by 3379.6. Now I have this output in terms of centimeter. 20 HP is equal to 4.35 centimeters in this graph. Now for the same length, for the length of 4.35 centimeter, you extend the line from the point A and name this point as A dash. Okay. Now we can, this is the line which indicates the full load condition of the motor for a 20 HP motor. But here this point is not on the semicircle, so we cannot predetermine all those parameters. Okay, so only draw a line parallel to this output line till it reaches the semicircle. Okay, so draw a line to this output line till it reaches the point P. Now from the point P, draw a line vertically downwards till it reaches the horizontal axis at point S. Okay. Now anything above this output line is the actual output. So the length PQ is giving us the output, and anything below this output line is loss. Okay, here only we'll be having this entire line indicates the copper loss, rotor copper loss, stator copper loss. Obviously we have not separated them, but still this entire length gives us the copper loss. So here in the same ratio, this QR is giving us the copper loss, and below that, that is RS, is giving us, this entire belt is giving us the constant loss. So here PQ is output, PS is the total input, because output plus losses is nothing but input. So PQ divided by PS will be giving us the efficiency of the machine. And they have also asked us to calculate the line current, okay, for the output, for the full load condition. This is full load condition point, and from point O draw a line to reach the point P, and this length is giving us the line current at the full load condition. Length OP, just measure the length of OP, which is 6 centimeter, but we want the line current in terms of amperes, so just multiply the current scale with that. We had taken current scale as 1 centimeter is equal to 5 amperes, so that is 5 amperes per centimeter. So this results in 30 amperes. So they had asked us to calculate line current and efficiency under full load condition, and here we have the results. Okay, few more numericals we will be solving in upcoming classes. Thank you.